You know when you see a demo for some new eye tracking system and it just looks perfect, slick, seamless, everything works? Have you ever thought, is that a little too good to be true? Well, you might be right. Today, we're going to pull back the curtain and look at the critical flaws that can make these polished, great-looking platforms produce data that is, frankly, scientifically worthless. Let's dive in. And the source material really hits the nail on the head with this quote. See, the real danger here is deception. A system can look absolutely fantastic in a sales pitch, checking all the boxes, but when you get it into the lab to do actual research, it just completely falls apart. We're about to find out exactly why that happens. So it really boils down to seven huge mistakes. We've grouped them into a few key areas just to make them easier to follow. We're going to walk through every single one so you can start spotting these red flags from a mile away and really understand what makes an eye tracking system genuinely robust and reliable.
So here's our game plan. We'll kick things off with the big picture, the demo deception. Then we'll get into the nitty-gritty with mistakes in time, followed by architectures that are just doomed to fail. After that, we'll talk data quality, and we'll wrap it all up with the bottom line from the experts.
All right, so this first part really frames the whole problem. We're talking about that huge, dangerous gap between a pretty user interface and scientifically valid, trustworthy data collection. They are absolutely not the same thing, and confusing the two, well, that's the first big step toward failure.
Let's move on to our first major theme, and it is all about time. Look, if you get the timing wrong in an eye tracking study, every single thing you measure after that, reaction times, pupil responses, you name it, is just fundamentally corrupt. It's that simple.
And here it is, mistake number 1. This is probably the most common and, honestly, the most damaging mistake of all, letting the user interface control the timing of events. Thinking that just because you tell a web page to show an image for 200 milliseconds, that it actually shows up for exactly 200 milliseconds? That's a massive, massive error, and it happens all the time.
Okay, so this lays it out, plain and simple, the bad way versus the right way. In a bad design, the UI, the pretty thing you see on screen, is calling the shots. This is a recipe for disaster. You get unpredictable delays, something called frame jitter, when the image kind of stutters. It completely trashes your timing. The correct approach, you have a dedicated execution layer that's like a master clock. The UI, it's just a display. It does what it's told, exactly when it's told.
The source does not pull any punches here. If your UI is running the clock, you're not just getting data that's a little bit off. No, you are getting, and I'm quoting here, garbage reaction time measurements.
Now, the second timing mistake is a bit more subtle, but just as bad. It's the difference between time-stamping your plan to do something versus time-stamping when that thing actually happens. It's like logging when you decided to show a picture instead of logging the exact moment the picture really appeared on the screen. Big difference.
And this right here shows you everything that needs a real, precise timestamp. It's not just one or two things. It's the whole shebang, the entire sequence of events in a trial, from the stimulus appearing to it disappearing, to the moment the person responds. Without these, you just can't calculate metrics you can trust.
Let's just pause on that for a second. It's such a powerful and simple rule. If timing is important in your study, and it almost always is, but you aren't logging the actual timestamps of these critical events, then your timing data, it's basically fake.
Okay, so we've totally nailed down why timing is so critical. Now let's look at how that applies to the system's architecture, its very bones, because poor design choices can make a system completely impossible to debug, reproduce, or, trust.
So a classic design flaw is just mashing everything together. Imagine trying to bake a cake where the recipe, measuring the ingredients, and the actual baking are all tangled up in one chaotic step. That's kind of what happens here when you don't separate the experimental design, the trial sequence, and the engine that actually runs it all.
So the right way to do it is with this clean 3-layer model. First, you have the protocol. That defines the what, the rules of the game. Second, the trial generator creates the how, the specific ordered list of trials. And third, the execution engine, our trusted timekeeper, runs that sequence with precision. That separation is absolutely key for a system you can rely on.
This next one is what our source calls a silent scientific failure, and that's a perfect description. Lots of systems run randomized trials, which is great science, but then they forget to save the exact random sequence that was shown to the participant. If you don't save that sequence, you don't actually know what experiment you just ran. And the consequences of this, they're catastrophic for research. You can't reproduce the session. You can't investigate a weird result that pops up. And crucially, you can't defend your data. Your findings become scientifically indefensible. So the bottom line is, if it was generated but not stored, it's lost, gone.
So we've got perfect timing, a rock-solid architecture. We're all good, right? Well, not quite. This next section is all about the data itself, making sure it's good quality during the session, and avoiding the huge pitfalls of misinterpreting what it all means.
It's such a common mistake to think of calibration as this one-and-done thing you do at the start of a session. But come on, people move. They blink, they slouch, they get tired. A good system has to be constantly monitoring the quality of the data it's getting, all the way through the experiment.
And here's why that's so important. This is such a great metaphor. If your data collection engine is basically blind, if it can't tell the difference between good tracking data and a bunch of noise, then any analysis you do later on is built on a foundation of sand. It's just waiting to collapse. Okay, now for a really dangerous leap in logic. So often teams will see some kind of eye movement abnormality, like say a high error rate on a task, and they immediately jump to slapping a disease label on it. They'll say, oh, that's Alzheimer's. This is a huge scientific error.
The right way to do this is methodical. It's disciplined. First, you establish a standardized measurement. Then, from that, you derive validated metrics, numbers that are rigorously proven to measure what you think they measure. Then you compare those against reference populations, and only after all of that can you even begin to think about what it might mean in a clinical context.
All right, our final mistake. It's a little subtle, but it is so critical. The rules you use for throwing out bad trials, a response that was way too fast or too slow, that's not just some data cleaning step you do at the end. Those rules are part of the experiment itself. They have to be defined up front and applied the same way every time. If you change them on the fly, your data becomes totally incomparable.
Poof! Okay, we've made it through all 7 mistakes. So let's bring it all home. Let's synthesize this by looking at all these failures through 2 different but complementary expert lenses, one from engineering and one from science.
Now what I love about this is how it neatly sums up the top 3 flaws from both sides. From the engineer's perspective, Professor David's view, it's all about reliable timing, proper storage, and quality control. For the scientist, Professor Jonas, it's about clean design, consistent rules, and being incredibly cautious with interpretation. They're 2 sides of the same coin. So if you remember nothing else from this explainer, please let it be these 3 golden rules. 1. The engine controls time, not the pretty interface. 2. You have to store what you show every single time. And 3. Keep your raw measurements completely separate from any kind of clinical interpretation. These are the non-negotiables.
And that leads us to the final, critical question you should be asking yourself. Whether you're buying a system, building one, or just using one for your research. After all of this, can you say with confidence that your system is built on a foundation of solid rock? Or is it maybe, just maybe, resting on sand?